Legged animals show remarkable agility and high dynamic movements, such as high-speed jumping through confined spaces. Reproducing these behaviors in legged robots has been a challenge, as it is highly demanding not only for the robot's locomotion but also for the decision-making abilities. In this work, we aim to realize similar lifelike agility on the quadrupedal robot, allowing it to achieve accurate narrow-gate traversal tasks under highly dynamic scenarios. The system is based on hierarchical reinforcement learning, which consists of a low-level and a high-level controller. Firstly, we train a low-level locomotion controller by imitating the legged animal's motions, which are collected in a motion capture system. This adversarial imitation learning uses a network-based discriminator and a style reward to ground the agent's behavior in the reference data. Another reward encourages the agent to accomplish the velocity tracking task. We finally obtain a locomotion policy that can track omnidirectional velocity commands and includes a wide range of maneuvers ranging from low-speed pacing to high-speed jump running. The skill transition is guided by the command velocity. The diverse motion patterns learned are due to significant differences in speed of different datasets. Secondly, the high-level controller is trained to select a feasible and collision-free trajectory to traverse the narrow gate by using the most appropriate maneuver sequence. For real deployment, a vision-based detection module is incorporated into the system to obtain the gate center and its geometrical information. The robot is initiated at a distance from the target gate and it uses the pacing to move towards the gate. In this period, the joint torques and angles oscillate within a moderate range. When it approaches the gate, we observe a very large stride of the two rear legs. The system enters the takeoff phase with the front legs off the ground and the torque of the rear legs' motors is nearly saturated. The robot is accelerated to a maximum speed of 2.5 meters per second in the flight phase and relies on inertia to move in the air. It undergoes fast deceleration in the landing phase and the torque of the front motors turns large to catch the fall of the robot. A quick shift back to the pacing gate is observed after a short period of recovery behavior. The gate information is obtained by the detection module at the beginning. Once the jumping is triggered, the planned trajectory of the feet effectors intelligently dodges the gate edge. In this process, the root height climbs up to 0.61 meter, nearly twice the initial height. During the landing stage, the rear calf joint bends close to the motion limit to avoid a collision. We further validate that our framework cons jump consistently outperforms other baseline methods. We demonstrate that the system also has the adaptability to changeable environments. The adaptive policy guides the robot toward the deviated gate position and jumps diagonally through it. This maneuver is more difficult than jumping straight forward as the area facing the robot is more constrained. More experiments in hardware and simulation are repetitively conducted to test the robustness of the gate position relative to the quadruped. Compared to the scenario of smaller gate height, when traversing a taller one, the controller autonomously allocates a longer takeoff distance in advance and makes more aggressive adjustments to the joint motion. Multiple complex terrain is generated to test the system's terrain adaptability. It can be seen that the high-level guidance module fully leverages the capabilities of the low-level locomotion policy, and the robot's behavior becomes more versatile. It can robustly conquer these complex environments while successfully accomplishing the narrow gate jumping task. The system also demonstrates reactive behaviors against emergent changes. The velocity command outputted by the high-level policy guides the robot to maintain its orientation toward the gate center. It shows nice overall tracking of the dynamically varying commands. The framework can easily be extended to adapt to new tasks by training a reconfigured high-level decision module without retraining the low-level locomotion policy. We design an extremely constrained scenario where the adjacent gaps within the fence can only accommodate the robot's 2 feet passing through separately. The reconfigured module successfully accomplishes these tasks. Please refer to our paper for more details.